Hi everyone. In today's class, I would like to explain program for traveling salesman problem using branch and bound. You know that a traveling salesman problem using branch and bound is very important concept in advanced data structures. In today's class, I would like to explain this program, which is in Python. So before going to explain this program, I would like to give you a small inputs about the Python language and the concepts that we used in this language for implementing traveling salesman problem. So let me get into the technical things. So before getting into this code, so I would like to introduce some of the concepts we used for implementing this traveling salesman problem using Python. Okay, so in the starting of the code, there are two lines called import numpy as NP, import sys. So we have imported two packages, numpy and sys. So numpy is a numerical Python, which is used for implementing mathematic related applications. In this particular program, we have implemented traveling salesman problem by using matrix. So in order to create a matrix, so we have imported that numpy package. And there is another a package called sys. So sys module is used for getting a large value in place of infinity. You know that in a traveling salesman problem we use infinity. So but in infinity we cannot compare, we cannot add or subtract the values. So we cannot add or subtract values, or we cannot compare the values using infinity. So for that, we whenever there is an infinity, so we replace that infinity with either with the zeros or with a large integer value. So for the purpose, we are importing this import sys. In this particular program, we designed a class called Traveling Salesman Problem Solver, TSP Solver. This is the name of the class. So in this particular class, we are using this NumPy. We already told that it's used for matrix operations. This provides access to system-specific parameters and functions, specifically for a maximum size constants. And in this particular class, there is an init method, which is a constructor, so used for initializations. You can see in this init method, there is a parameter called cost matrix. And there are data members like n, cost matrix, visited, final result, final path. Here n is used for storing number of cities. You know that in traveling salesman problem we take a set of cities, and those are connected by the paths or edges. Our task is like we have to visit every city in the graph only once, and we need to cover every city, and we need to come back to the starting city. That is our task. So here the number of cities are represented with n. So self dot n is for number of cities, and we want to represent the distance between the cities as a matrix. So we call this as a cost matrix. So cost matrix is converted into numpy kind of a array. So later we do that. And there is a list called visited. So it maintains all the uh, cities, whether they are visited or not. If a city is visited, we store true value. If a city is not visited, we store a false value into that. So in this particular program, we will take 5 cities. So there will be 5 entries in the visited list. And there is a final result. So that will hold the minimum cost. The task of our program, or the task of our traveling salesman problem is we need to find out what is the minimum cost required to visit every city, so that we need to visit every city so that we exactly visit a city only once, and visiting every city and coming back to the starting city. So the final result will be stored in this particular data member called final. Res means result. And there is another data member called final path. We need to disclose like what is the path, like from which city we started, and the path we need to show that from which city to which city we are actually traveling. And finally, um, to which we are actually coming back. So we need to show that as a path. So that value will be stored in this final path. So these are the various data members used in the init method. And there is a function or a method called matrix reduction. So the matrix reduction is, we know that in traveling salesman problem, we need to reduce the matrix, um, like towards the row values and as well as towards the column values. So row wise and column wise, we need to reduce the matrix. That means we need to make the matrix at least 1 0 should be there in every row and at least 1 0 should be there in every column. So that's how we do that actually. This particular method is for doing that. That is for matrix reduction. Okay. So what do you mean by row reduction is subtracts the minimum value of each row from the all elements in that row, and column reduction is similarly subtracts the minimum value of each column from the every column. Okay, then cost calculation is keeps track of the total cost of the reductions, which helps in estimating the bounds. And there is another method called finding minimum cost. So before starting the traveling salesman problem, we need to find out like what is the minimum cost. Okay, so that is actually performed with a method called find min. So this find min, this function finds the minimum cost edge for a given row I. So like for every row I, we need to find out like what is the minimum value. So that can be found by using this find min. And there is another method called calculate initial bound. So calculate initial bound, this is the another reducing matrix, like this reduces the initial cost matrix to obtain the starting lower bound for the problem. Like before starting into the matrix, actually we need to find out the what is the lower bound to start the application or to start the problem. So that can be found by using this method called calculate initial bound. And as we know that traveling salesman problem is actually solving here with the branch and bound. So there is another method called ESP, traveling salesman problem, branch and bound. So which is taking different parameters like level, current bound, current cost, current path, and reduced matrix and all. So this is another important function. This is the actual recursive function, which is actually the main heart and soul of the total implementation. So this will find out the total concept of traveling salesman problem. Like it starts with the base cases, like when all cities are visited, it checks the cost to return to the starting, and it recursion, it applies recursion, like it iterates through the unvisited cities and explores possible paths using a depth first search. Okay, so it uses the concept called depth first search, like visiting every city, and finally it will return the final cost that we actually need to implement this concept, right? So this is the main method. Okay, and the code is actually initiated with another method called solve method. So this is solve method is the code like this. Okay, we'll come to this particular code later. Okay, so it's a sets of initial conditions and calls the recursive function to start solving the travel assessment problem. So running the code with given matrix, and let's analyze how this would work with the provided cost matrix. Okay. So actually in this code, actually we are actually taking a cost matrix, something like this. Here you can see the cost matrix. Okay. So there are 5 rows. There are 5 rows and 5 columns. So this is actually 5 by 5 matrix. So number of cities is 5. So with this cost matrix, you can assume that there are 5 cities. So we need to find out like we need to find out a path starting from one city and visiting every other city only once and coming back to the starting city. So this is the actually the matrix that we want to give it as an input to the code. So the first thing is like we need to initialize the matrix reduction. So the cost matrix will be reduced using the reduce matrix function, which will find the minimum values in rows and columns and adjust the matrix. We know that traveling salesman problem is actually solved by reducing the matrix row wise and as well as the column wise. The logic is like we need to find out the smallest value in every row, and we subtract that smallest value from every other column in that row, so that there will be at least 1 0 in the row. Similarly, we apply it for the columns. We need to find out the smallest value from every column, and we subtract the column values from that smallest value, so that every entry, at least one entry in the column will be 0. So that is the thing. Actually, we perform that reduction of the matrix. Then we do that calculation of initial bound. So the calculate initial bound method will give us the initial bound based on the reduced matrix. So what do you mean by initial bound is like we need to find out the sum of the low row values and some of the low column values. So that can be set as an initial bound. Then we need to explore the paths. So the TSP branch and bound method is there. So that will begin exploring paths starting from city 0 and mark cities as visited. So these 5 cities we can we can represent them by using numbers from 0, 1, 2, 3, and 4. So the numbering will be from 0 to 4. So it will keep track of the current cost and bounds to prune branches that exceeds the known best cost. So what happens here is like whenever we want to go to a particular level, so by finding all the cost values, so we choose the branch with the least cost. So here we apply actual least cost branch and bound. So we ignore all other cost values. We proceed with the branch which is having the least cost value, and the final output will be like once all branches have been explored, the final optional cost and path will be returned. So the expected results will be like after running the solve method, you will get the optimal tour cost and the total optimal tour cost will be 28 for the given matrix that we have already seen in there. And the route will be like 0, 3, 4, 1, 2, and 0. So that will be the route. We start from vertex 0 and go to vertex 3, then 4, then 1, then 2, and we come back to 0. So that's how we visit all 5 nodes only once and come back to the starting vertex 0. So before getting into the program actually, so I would like to give some inputs about some of the key concepts that we have used in this particular program. So you can see that the ones with the blue color are the statements from the code, Python code. So I'll just give you the input like what is the meaning of that each and every line. So there is a line called np-min array axis equals to 0. So this operation is calculates the minimum value along the columns. So that is from the vertical direction. For the above array, it would return 1, 2, 3, which are the minimums in the each column. Like what does that mean is like np.np stands for numpy. So there is a built-in method called min. And for this, we need to give two parameters. One is the array, the cost array, and another one is the axis 0. So axis 0 means it will calculate the minimum value, like min function will find the minimum value among the columns. So axis 0 means we're actually finding the minimum values among the columns. So that is in vertical direction, right? So another line is called np-min array axis equals to 1. So when axis equals to 1, we are actually working on the rows. So in traveling salesman problem, what we do is like for every row, we need to find out the minimum value. So that can be found by using this notation called np.min, numpy.min on array with axis equals to 1 means for every row, that is like a horizontal direction. So these are the some of the statements that we have actually used in that. Okay, so you can simply remember like this: axis equals to 0 means we perform the operations along the columns, and axis 1 means we perform the operations along the rows. And there is another statement called row min. Row min equals to np.inf equals to 0. So what is this particular line is this line replaces any occurrence of np.inf, that is infinity, in the row min array with 0. We know that in traveling salesman problem, in some of the rows and columns, we have to use infinity value. So here the infinity value is actually represented with np.inf, that is infinity value. So whenever there is an np.inf value, we cannot compare that value or we cannot work with that value. So for simplicity or to reduce the calculations complexity and all, we have to replace that np.inf with 0. So for that, we actually doing this row min. Row min is whenever is equals to np.inf or row min value is infinity, then we are replacing that infinity with 0. So why we are using the zero means, so setting infinite values to zero allows the algorithm to effectively ignore those rows during the subsequent reductions, and whenever you later subtract this minimum from the matrix, it prevents the algorithm from introducing further complications. So in order to reduce the complexity and the complications, we actually replace infinity with the zero. So that is the primary motto of writing this statement. And there is another statement called np dot new access. So this np dot new access is actually called as the broadcasting. So we use it for the reshaping the arrays. Okay. For example, what is this np dot new access is like, it's a kind of a special indexing mechanism in a numpy we use. So what it does is like, it allows you to increase the dimensions of the existing array by adding a new access. So remember that, for example, if there is an array with a single dimension, that means only one row is there, and we want to add another dimension to the array, like we want to add the column also, so we can use this new access. So what that becomes is like, a one dimensional array will be converted into a two dimensional array. So for that purpose we use this new access. Okay, here I am actually showing with an example. You can see here, like, here there is a one-dimensional array. So for example, row min equals to np dot array 147. So there are three elements in a one-dimensional array, where is there is only one row. If I write it as a row min reshaped, like means we are taking another name, row min reshaped equals to row min of colon comma np dot new access. What happens is this 1D array will become a 2D array, where there will be three rows, and in every row there will be one column. So 147, which are actually in a single row, they will actually reshape it into, in first row there will be one, in second row there will be four, and in third row there will be seven. So this will be like a 3 by 1 matrix. So actually the one dimensional array with the size 3 is actually converted into a 3 by 1 array. So for this actually we are using this new axis. Okay, so what is this purpose is actually is like, we will find out the values, like the smallest value in every row, which are actually in a kind of a single row, but we need to consider it as a vertical kind of a array. So in that case we use this actually. And another sentence where we actually using a kind of a different notations is like, there is a self dot cost matrix ij. If self dot cost matrix ij not equals to infinity, else system max size for j in range self dot n. So this is actually a kind of a list comprehension we are actually using here. You know that a list comprehension is an easy way to adjust the create the list with so-called predefined conditions. So what is the meaning of this particular statement is, if the cost at a self cost matrix ij is not infinite, it takes that cost. If the cost is infinite, it substitutes the system's max size, which is very large number. You know that like in the cost matrix, there can be values. If there is no infinity value, we consider that value. If there is an infinity value, we actually replace that with a large value. So which is actually called as a sys dot max size. So that is the purpose of this particular line. And there is another line which is new matrix current path level minus 1 comma colon equals to np infinite. So what is this is like, here the algorithm set all values in the row corresponding to the last node visited in the current path to the infinite. We know that in traveling salesman problem, what we do is like, if there is an edge from uh, vertex 1 to vertex 3, what we have to do is like, if there is an edge like 1 comma 3, what we do is, in cost matrix, if this is 0 1 2 3 0 1 2 3, so in a row 0 we have to put all infinities like this, and for the third column we have to put all infinities like this, right? So this is actually we can done this with these statements, and we need to say that like, we are actually taking like a 1 to 3, so that means 3 to 0 should also be like infinity, like we should make that value as a coming back to 0 is the first value, like 30 value should be in put to infinity. So this is actually we are doing here. So we discuss this when we go to that particular code and all. So here you can see this. There are three statements actually. One is the new matrix current path level minus one. That means in the previous values or in the previous calculations, we have to, the corresponding rows values should be put to the infinity values. And the new matrix colon comma I means, so this lines sets all the values in the column corresponding to the current node I to infinity. So I said that like we need to make one row all infinities and second column as all infinities, and we need to put that new matrix I comma 0. So in this line, the algorithm sets the cost from the current node to back to the starting node should be also be 0. Okay, so these are the points. Like I said, like in this particular thing, we need to put one row as all infinities and one column as all infinities, and current node to the starting node should also be this. So this is the row and this is the column and this is the current node to the starting node. So that's we have to do this kind of things. Like, so for this purpose we used that kind of a list comprehension, a list slicing, and as well as different kinds of numpy operations. So these particular three lines actually used for that purpose. Okay, so these are the different statements that we have actually used in the code. Now we'll go back to the actual program. So I think I have given you enough inputs to understand this code. So this is a traveling salesman problem using a branch and bound. So here you can see that the first line is we are importing a numpy. We are importing in numpy. So I said that numpy is used. Actually, we are using here the matrix values, and the mathematical calculations or matrix operations are easy with the numpy package. So we're importing that numpy package and module. So, and for the large integer value, we are importing the sys value, right? So this is the class TSP class, traveling salesman problem solver. So this is the constructor. So we know that constructor is for initializing the object, right? So whenever an object is created, n value will get the cost matrix length. So cost matrix length is like, here we use actually 5 by 5 matrix. So n will become a 5. So then there is a cost matrix actually converted into NP kind of a array, and we will create a list which maintains n number of values, and every value is initialized to false. Okay, and there is a sys max size like a final result, and there is a path we need to create it as a list. So this is the like initial values. So we'll just start with like how this execution starts. We know that every program execution starts from the mainline code. Okay, so here the mainline code is actually the input matrix, cost matrix. Okay. So this is the mainline code. Okay. Mainline code. So what is the first statement in mainline code is like we are actually giving a cost matrix. So there are 5 rows and 5 columns, 5 columns. So this is a 5 by 5 matrix. We are calling it as a cost matrix. Okay, so we are initialized that cost matrix values, like the graph is actually represented with this cost matrix values. So what does this 20 means? 20 means this is like, what is this is like this cost matrix is like this. There are 5 cities: 0, 1, 2, 3, and 4, and 0, 1, 2, 3, and 4. So the first value is np.inf, means this is infinity. So the edge from 0 to 0 is infinity, and the next value is 20. So what does that mean is, if there is a graph like vertex 1, vertex is 0, and there is a graph with 1, so the distance from 1 to 0 to 1 is actually 20. What does that? So that is the meaning of the value 20, and there is a 30 in the second row. So that means there is another vertex called say 2, and the cost or the distance is like 0 to 2 is 30. So this is like how the values are actually assigned: 10, 11. So, and from 2 to, like from 1 to 0, it's actually 15. So there is another path from 1 to 0. So this will be like a 15 and all. So this is how these values are actually created. Okay, so I'm just erasing these things, like we'll just confused by seeing all these things. Like, so I think you understood like what is this cost matrix. So cost matrix is like a row number of cities are actually used for both rows and columns. So since there are 5 cities, so 5 rows and 5 columns are there in this cost matrix. So then we have, what we do is like we will create an object solver. So we'll create an object solver. So solver is an object. So this solver object, we are actually calling the TSP solver, which is the name of the class, and we are sending this cost matrix as a parameter. So from this, we'll go to the init method of the TSP solver class. So here you can see this. This is the TSP solver. So this is the TSP solver. So this init method will be get executed because we have created an object called solver. So this solver is this object solver. So here n value is the length of the cost matrix, that is the 5, and cost matrix will be like previously I said, no, there will be infinity, 20, 30, 10, 11, something like that. So that will be actually stored as a cost matrix. And there is a list called visited. So what is this visited is like there are 5 cities, so there will be 5 blocks. The index values is from 0, 1, 2, 3, 4, and all the values will be initialized to the false because here we have initialized false, and there is a final result. So there is a data member called final result. So this is actually initialized to the maximum value means infinity, and there is a final path, and final path is also a 5 value list path. Okay, so this is an empty list for 0, 1, 2, 3, 4. Okay, so this will be like this. Okay, this is like how the solver object will be actually initialized. Okay, we created an object. So this particular line actually initializes the object called solver. That is actually we actually draw just now. Then what we are doing is with this object solver, we are calling a method called solve. And that solve method will return 2 values. One is optimal cost, another one is optimal path. So this solve method will return 2 values. So first value will be optimal cost, that will be the answer, and optimal path. Finally, we will display the cost, optimal cost, and optimal path. So these are the things like, so now what happens is we have to go to the method called solve. So solve is here. So solver.solve will brings you here solve method. So we don't need any parameters for this. Here, what is that is like the first line of the solve method is we are calling calculate initial bound. We know that in traveling salesman problem, first we need to reduce the matrix and we need to find out the initial bound value. So we just calculate that initial bound value with the help of a method called calculate initial bound value. It also returns 2 values. One is reduced matrix and another one is the initial bound values. So one is the reduced matrix and another one is the initial bound values. So now we have to move to the method called calculate initial bound. So calculate initial bound. So we'll go to calculate initial bound. So this is the calculate initial bound. So in the first statement of this calculate initial bound method is So it is actually calling another method called reduce matrix, and it's sending the cost matrix copy. So cost matrix is the one like we allocated the values in the initial, and we don't want to disturb its values. So we will create a copy of the cost matrix copy. So copy will be created and that will be sent to the another method called reduced matrix. It also sends two values. One is the reduced matrix, and another one is the reduced cost. Now we move to a method called cost matrix. So the cost matrix function is, we will go to the function called reduce matrix. So we go to the reduce matrix with the parameter cost matrix copy. So reduce matrix method. So this is the reduce matrix method. Okay, so here you can see that reduce matrix method is taking the one parameter matrix. That matrix is actually the copy of the cost matrix, because we don't want to change the initial values. We don't want to alter the initial values. So we created a copy of the initial cost matrix and we are sending it to the method called reduce matrix. So what is this reduce matrix is like it performs two things. One is the row reduction and another one is called the column reduction. I said like row reduction means in every row we need to find out the smallest value and we need to subtract that value from the every value in that row. So that can be performed with these numpy values. So we already saw that there is a method called min method which can be applied on np or numpy. So and axis 1. Okay, axis 1 means like on every row value it will find out that row minimum value, and that row minimum value, if there is an infinity value, that infinity value is substituted by 0. We already said that we cannot compare or add or subtract infinity, np dot infinity. So in that infinity value is replaced with 0. Then row reduction cost will be like we will add all the values like the minimum values, row min values, and we perform that sum operation that will give you the sum of the all minimum row minimum values. So that will be like a row reduction cost. Then we create a kind of value like kind of we need to shape the matrix value like a row wise matrix can be reshaped into two-dimensional array. We already saw that this is called np dot new axis, which converts your 1D array into 2D array. So we'll convert that value and we subtract the matrix from that row min values. Then we do the column reduction. So this is similar to the row reduction. So if axis value is 0, it will perform the column reduction. So for axis 0, we find all minimum values. So that will be column minimum values. That column minimum values, if contains the infinity values, that will be replaced with the zeros. Then the column reduction cost is like a sum of the all the column in values. And what we do is like we just subtract that column in values from the matrix. So how we get the total reduction cost is like we add the row reduction cost and as well as the column reduction cost. So row reduction cost plus column reduction cost, we add those two things and we return the values like the matrix and as well as the reduced cost value. So this will come back or come back to the one that like from where we actually went to this particular method called. So we'll come back to this particular place. So that matrix value will be stored here and reduction cost will be stored here. And the next statement in this calculate initial bound values is return reduced matrix and reduced cost. So this reduced matrix and reduced cost will come back all the way down to the place like from which where we actually went to that method and all. So that will come back to here. So matrix will come and stored in this reduced matrix, and the initial value cost value will be like initial bound value. So we'll come back to the method called solve. So the next statement here is like the current path. So what is the current path? We actually have to maintain like a path and all. So current path means like for every city we need to maintain whether we have visited or not visited. So since there are 5 cities, so all the values will be initially initialized to -1 values, -1 values. So that is a n into n means 5, 5 into -1. So 5 -1 values will be get stored in current path. And we have to start from a particular node. Here we want to start with the node 0. So source will be the node 0. So source will be the node 0. So that is the current path will be like 0. So this -1 is actually stored with 0. That means we actually started from the node 0. And we say that this node is actually visited. So in the visited uh, array, I said you like there is a list called visited, like this, visited. So there will be 0, 1, 2, 3, 4. We starting from node 0 means we actually visited this node. So we'll make this as a true. So that is that we visited of index 0 equals to true. We make that true, that is we visited it. Then what we do is we call the recursive function, that is the main heart of the logic of this particular traveling salesman problem, that is the TSP branch and bound. So we call the TSP branch and bound, traveling salesperson branch and bound, and we send different parameters to that actually. So here you can see here, like the first parameter here is the first parameter here is 1. 1 means we go to the next level, because in the graph we started from 0. So we'll go to the all the vertices which are connected directly with the 0. So here that is actually 1. And then we send this initial bound value, whatever the initial bound value we got, we send that. And then we start the previous node, that is actually 0, because we started from 0. And we also send this current path value. Current path is this one. The index 0 will be like 0 and all are -1 values. And we have to send the reduced matrix. The reduced matrix actually we got from the previous function call, so that we actually send. So now the control goes to the main function, that is called the TSP branch and bound. So what is this TSP branch and bound is? So this is the TSP branch and bound. So we'll come to this particular place, TSP branch and bound. So all the parameters we actually passed from that function call actually copied into the parameters here. So here you can see all the logic of the traveling salesman problem. So here the logic is like if the level is equals to self.n is a 5. So the initial level value is actually we send actually 1. So 1 double equals to 5 is actually false. So this particular thing don't work actually. So this will be like executed when we completed the entire tour, like when a level becomes a 5, so then self n equals to 5 equals to 5. So this particular condition will be true for the last statement, right? So this is false, so we don't get in there. So we start with the for loop. So what is this for loop is for I in the range self dot n means 5 values. So this for loop will run for 5 times. So for every round, what we do here is like here you can see that if not self dot visited of I, right? If self dot visited of I means a 0. So if the 0 is not visited, so that is actually false. So we'll come back and I will get the values. I will get 0, 1, 2, 3, 4. So actually 0 is visited, so that will be false, and will come again for the for loop and I becomes 1. So visited of 1 is not visited. Yes, that is true. And self cost matrix of the current path, the previous path, and of I. So here you can see that here what we are doing here is like if that path is not infinity, like what is that mean is actually if there is a node called 0 and there is another node called 1, and there is a path from 0 to 1, and if this 1 is not visited, yes, if it is not visited, we started with 0, so this is not visited. And if the distance from 0 to 1 is not equals to infinity, that means there is a valid distance from 0 to 1, then this will be true. So actually from 0 to 1 there is a value 20, so that is actually true. So we actually come to this particular place here. The current bound value which we received from the function call will be come here, and that will be stored in the temporary bound. So the current bound value is actually stored into the temporary bound value, and the temporary cost will be calculated as a current cost plus self cost of the matrix of current path level minus 1. So this current path level minus 1 means the cost matrix of from the previous step. So, and that is added to the current cost, and current cost is the one from that we received from this parameter. So current cost is added to the cost matrix from the previous step, and that will be the temporary cost. Okay. So what we do is like again we calculate a copy for the reduced matrix, because we don't want to alter the current matrix, because we need to save the cost matrix of the previous step every time. So we create a copy of that and we give that name as a new matrix. So what is that? Is that new matrix here? Here what we do is like if the current path of the previous nodes, we what we do is like we have to make that the row values on the, if there is an edge from 1 to 2, we said like if there is a edge from vertex 0 to vertex 1, so what we have to do is like row 0 all should be all infinity, and column 1 all should be infinity, and the edge from 1 to 0 is also should be infinity. So that is the main concept in the traveling salesman problem. So whenever you take an edge, what we do is like the starting vertex will be applied to the row and make all the values in that row to infinity, and the other vertex from that edge, that is 1, and the column value of 1 should be all equals to the infinity, and the from 1 to the initial node, that is 0, that's value like 1 0 should be like 0. So what is this? What we are actually doing here is with these three statements, this and the previous statement, what we are doing here is, so in this particular cost matrix, so 0th row, all 0th row values should be infinities, and all 1 columns should be infinities, and 1 to 0 should be infinity. 1 to 0 should be infinity here. 1 to 0 should be like 1 to 0 should be infinity. 0 1 2 3 4, and 0 1 2 3 4. So what we have done is like 0th row we put all infinities, and column 1 we put all infinities, and from 1 to 0 this value should be infinity. So that is actually we are performing with these statements. So that is the meaning of these statements. So if you know the traveling salesman's concept, problems concept, you can easily understand the concept of these things, why we are doing actual these steps and all. Then what we do is like we have to find out that reduce the matrix, and we send this matrix to the reduce matrix function, and the parameter is the new matrix value, and we send it to there. Then we get again a new matrix with the reduction cost. So what we do is like we add that reduction cost that we received from the reduced matrix to the temporary cost. So temporary cost plus equals to the reduction cost. So we have to add the cost values. That means we need to update the cost values we got from that. Then we, the temporary bound value will be the current bound plus the reduction cost. So here the temporary bound values will be current bound plus reduction cost. So what we do is like we have to compare this with the already final result value. So this is actually done in the last step. So what is that is like if the current temporary cost is less than self dot final dot result, then for the current path for the level 1 will be I, and the visited I will be true. That means 1 is visited. And here what we do is like again we call the TSP branch and bound, because we said that TSP branch and bound function will be a recursive call. So again this call itself, and what we send is like we are actually worked on the level I, so we have to send the next, so the current level plus 1, so we are moving to the next level plus 1, and we send these temporary bound values, temporary cost values, and current path and new matrix as a parameters. So this is like a recursive call, so it calls itself actually, so it go back to the its own definition, like this. So it again it comes to this particular place. We know that if you know the theory of the concept of a traveling salesman problem, we need to do the same operations again and again for different rows and different column values for all possible edges. So that is actually what happens here. And finally this TSP branch and bound method will compare each and every row and all, and in the path every node is added and in visited, if all the nodes are marked as visited it as a true, and the path is like we are coming back to the initial vertex like 0, so that will be the end of the total concept. And finally this particular thing will send that final cost and final path to the mainline code. So here you can see that this solve and solver dot solve will send the optimal cost and optimal path, and finally we just print the optimal cost and optimal path. So here in this particular example, that is actually the optimal cost will be like 28, and the path will be like this. I'll show you execution of this particular code. So here you can see this is the code, the traveling salesman problem code. So I'll just run this. So here you can see that the optimal tour cost is 28 and optimal tour path is 031420. So that is the output. So this is the implementation of traveling salesman problem using branch and mode. Hope you understood the concept. Thank you for watching my video. Bye.